All right, this is should be familiar to you. This is very similar to what we did for compression elements that are subject to axial compression or columns in Chapter 4. In Chapter 4, we looked at just one slenderness limit on width to thickness ratios, and we decided if a element was non-slender or slender. Non-slender being the better part and slender being a little bit more involved. With beams, it's pretty much the same process, except instead of just one limit to check, we have two, because we could have compact, non-compact, or slender elements within a shape. Okay, and again, it's going to either be a compact section, non-compact section, or a slender section. Depends on the worst condition, right? So slender is worse than non-compact. Non-compact is worse than compact. So going the other way, compact is the best. Non-compact is not so bad. Slender can be kind of a hassle. Okay, so with beams, what's a little bit different is we use again. Oops, sorry. Let me go back. Beams, we're going to use two checks, right? So we're going to have lambda sub p, and we're going to have lambda sub r. If our lambda, which is just a general width to thickness, okay, so any width to thickness that we have, be it flange or be it web, any width, I should write neater, but it's difficult, to thickness, that's what we call lambda. If lambda is less than lambda sub p, it's compact. That's good. If lambda is greater than lambda sub p, but less than lambda sub r, all right, if I think of three regions here, this is non-compact. And then if lambda is greater than lambda sub r, then it's slender. And that's makes that element a little weaker. Okay, so this is just checking for local instabilities. Okay, so we are definitely looking at things like the B sub f, the flange width, and the flange thickness, and then we have H, all right, and then we have T sub W. So flange thickness, we're going to take B sub, or flange width, we're going to take B sub f divided by 2, because we really just want this distance, right? And then divide by T sub f, and that's going to be lambda of the flange. Okay, and then lambda of web would be H divided by TW. Okay, and you can calculate those, or if it's a standardized shape, there's tables in the table 1.1 shows you these values. But if you were doing built-up shapes, you would have to calculate it. Okay, so if we look at T1, table 1.1, right, here's the compact section criteria. So there's what I just wrote, the B over 2T sub f and H over TW. Okay, so we don't have to calculate them, but you need to understand how to calculate them for sure. Okay, so now if we move into the specification, right, this table is based upon the specification, just the parts that we need for a wide flange shape. Again, our objective is to decide is the cross section compact, non-compact, or slender. It's going to be governed by the worst case scenario between the flanges and the web. Okay, so then we look at this web, they are unstiffened, right? Or I'm sorry, flanges are unstiffened, okay, and web are stiffened elements. Again, if you have to review that video associated from or provided by AISC. Okay, so flanges are unstiffened elements, webs are stiffened elements. And this information comes from the AISC specification. table B 4.1b. Again, for columns, we looked at B 4.1a. Okay, but now we're looking at B because we're dealing with compression elements subject to flexure. Okay, and again, see, we have lambda sub P, we have lambda sub R for unstiffened elements. Right, unstiffened elements are flanges of hot rolled shapes, I-channel sections, or I-shaped sections, channels, and T's. So here's our limits. And again, notice it's always multiplied by the square root of E over Fy. Okay, so this is a constant per the material. What changes is the factor out in front. Okay, so this is unstiffened elements, and then stiffened elements are going to be webs, right? Because they're attached to plates being the flanges at either end. Again, still a function of square root of E over Fy. So we're just going to multiply by different values there. Okay. So I think I'm here. Nope. Okay. So all that. And then this, oops, let's back one up. Then table 1.1, again, we get the, we can get the B sub F over 2T from these values, right? From this column in the tables. Okay, so now, again, if lambda is less than lambda sub P, oops, all right, if lambda is less than lambda sub P, it's compact. If lambda is greater than lambda sub P, and I guess you could say equal. If it were equal, I'd want to go compact because that's the better condition. Or if lambda is less than or equal to lambda sub R, then it is deemed non-compact, and that's a different part of the specification. If lambda is greater than lambda sub R, then that element or cross-section will be determined or be classified as being slender, and you'll have to find the appropriate sections of Chapter F for members with slender flanges or slender web. Okay. So again, this stuff all comes from this table. Okay. It's just easier. It's formatted here for us. Okay. So hopefully that's familiar, very much like columns. Okay. So again, whenever we check a shape, it's going to be controlled by the worst case between the flanges and the web. Again, compact is the best. That's what we prefer. That's better than non-compact, which is better than slender. Okay. So whichever one is the worst condition between the flanges and the web, that's what controls the classification of the cross section. Okay. So let's do a quick little problem here. All right. So we have a W at 21 by 48. F sub Y is 36. So this ratio of this ratio here is constant for all parts of the shape. So I'm just going to calculate that out. 29,000 divided by 36, and that ratio is 28.38. So we can take that number stored in our calculator and just multiply everything by the factor out in front of the radical. Okay. And that makes life a little bit easier. Okay. So we can take 0.38 times 28.38, and that limit is 10.7. So if lambda is less than 10.7, the flange would be classified as being compact. Okay. Okay. If it is 1.0 times 28.38, that's the upper limit. So this is obviously 28.38. If the lambda is in between here, then so if lambda is greater than lambda sub p but less than lambda sub r, it's going to be non-compact. And then if lambda is greater than lambda sub r, it's slender. Okay. Down here, 3.76 times 28.38. That limit is 106.7. And this is 5.7 times 28.38. And that limit is 161.1. So now we have our cutoff points, right? So these are our dividing lines between compact, non-compact, and slender. So now we need to just find the values for the W21 by 48. So we can go back to our table. 21 by 48's right there. So our two values are 9.47 and 53.6. So 9.47 and 53.6. All right, so this is lambda of the flange, all right, which is b sub f over 2t sub f, and this is lambda of the web. So here, 9.47 is definitely less than 10.7. So this web, or flange, excuse me, is compact. All right. Golly, what did I just do? There. So flange is classified as compact. Certainly 53.6 is less than 106. So this web is also compact. So they're both compact. So that's the best we can hope for. So therefore, the shape W21 by 48 with Fy of 36 KSI is compact. That's our answer. Okay, that would be our answer. So W21 by 48 made out of 36 KSI steel is classified as being compact. Okay. Again, just say it. Web by and large are going to be compact up to 70 KSI for all rolled shapes. Some web or some flanges will be in this non-compact area. Okay, so if our lambda sub flange were 12, we would be in between 10.7 and 28.38. So that would be a non-compact flange, and that would control the classification of the shape. Okay, so that's that. Again, contact me if you have questions.